Good evening. I'd like to present my second project for applied statistical methods on the simple linear regression of the age of carpets through the decomposition of cystine and its content as a function of time. So, a Hungarian chemist wanted to research if there was a relationship between different chemicals which are found naturally in wool and their decomposition or accumulation through time to determine the age of antique carpets and other antique textiles. So that was the original research question that these chemists had, are what are the different chemical compounds that we can trace as a regular function of time. So one of the chemicals that they focused on after analyzing a number of carpets is cystine, which, as you see on the left-hand side, is a compound that has two sulfur atoms that are linked together. And then the cystine, the chemical pathway on the right, shows an oxidation of the cystine to cysteic acid. So does the cystine, which is found in wool, does it decompose in a predictable way as the carpet ages that you could make preferably a linear function, but some sort of function to relate the age of the carpet to the cystine content? So the original data that came from the researchers has about 23 carpets, all of age ranging from present day to over 1700 years, and then 4 different chemical compounds: cysteic acid, cystine, methionine, and tyrosine. Personally, I wanted to show the correlation between cystine and age just because cystine has a fairly well-known decomposition path, but there are some other options that one could analyze if they wanted. So this is the plot of how cystine content decreases with age. It's fairly linear. You can see a slight bit of curvature to the data, and then a few outliers, especially at the carpet, which is not aged at all on the left-hand side. There's a dot that has a very high cystine content that's an outlier that will actually affect the data quite a bit later, we'll see, but generally a nice linear trend. So just a little bit of background of simple linear regression. I know that we're all aware of it, having taken applied statistical methods, but just to demonstrate my understanding, simple linear regression, you basically want to form a straight line trend with the data, and you can take XY pairs of the data and correlate them with beta parameters and then an error term, that epsilon sub I term, as the top line shows. And you determine your beta parameters by minimizing the sum of the errors squared, shown on the bottom line. So for this analysis, we want Y to be the cystine content, measured as a concentration, and X as the age of the carpet, which seems a little counterintuitive, but that's how the paper originally analyzed the data, and I wanted to keep in line with the way the paper analyzed the data. And of course, the all-important assumptions of simple linear regression tied into this notation here. You, of course, have to have, first off, normally distributed errors. They have to be independent. They have to have a mean of 0 and a constant variance, which we'll see that there are some errors with these error assumptions and some of this analysis, but those get smoothed out as the presentation proceeds. So first I wanted to show how the errors, or the assumptions about the errors, don't conform for the simple linear regression with all 23 data points in. The p-value for the Shapiro-Wilk normality test is telling us that the errors are not normally distributed, and this QQ plot here is not the nice straight line that we would expect. So unfortunately, SLR for all 23 data points is not what we would like for it to be, but I continue with the SLR. And then also to further show that the assumptions for SLR aren't quite valid, here's the plot of the residuals against fitted data points. However, it has a fairly apparent a quadratic shape to it, which suggests that maybe a quadratic model would represent the data better. So the linear model itself, this was the result of the linear model. You can see that there are some points which lie above and below the line, but the quadratic characteristic it becomes more apparent whenever you try to force a straight line through it. However, the adjusted R squared is still fairly high at 0.96, so the line is not a bad fit. And a practical interpretation of this trend is that cystine content is at a maximum whenever the carpet is not aged at all, and then decreases, which of course we already could have inferred through the chemical pathway. And even though we did not meet the necessary assumptions for SLR, and even though the linear model is not the best model, the confidence interval for our beta parameters still show that both beta naught and beta 1 don't have 0, or we reject the null hypothesis of 0 for both the beta parameters. So even though the linear model is not the best fit, the beta parameters still seem fairly reliable. However, the Cook's plot shows us that the 23rd data point, the one which I originally mentioned with the carpet that had not aged at all, is a very, very strong outlier. So we proceed to eliminate the 23rd data point, reanalyze the normality assumption with Shapiro-Wilk again, and find a p-value of 0.02. So we still, unfortunately, if you pick an alpha of 0.05, you still have to reject the null hypothesis that the errors are distributed normally, but the p-value is increasing, so the linear model seems to be a better representation. And then the plot on the right is showing the old line, and the turquoise there was the simple linear regression with the 23rd data point, but with that point removed, we have the purple line, which doesn't change drastically in slope or in intercept, but a little bit. But there's still a quadratic characteristic to the trend, so I go ahead and next do a quadratic model with all 23 data points. But we still, whenever we do the quadratic analysis, there's still that data point, that very first data point, that shows up as an outlier, and in fact it appears to be an even worse model with the quadratic model, or worse outlier with the quadratic model. However, even with that outlier included, we still have an R squared of 0.9845, which is higher than before, so suggesting that we're moving in the right direction by going with a quadratic model. And also, the p-value is 0 for Shapiro-Wilk, so we again have to reject the null hypothesis that the errors are distributed normally for the quadratic model with the 23rd data point. But if we remove that outlier, then we have a very nice quadratic fit with an R squared of 0.9933, the highest of all the adjusted R squareds so far. And moreover, the Shapiro-Wilk test for the quadratic model with the 23rd data point removed gives us a p-value of 0.303. So in fact, we do meet and conform to the assumption that errors are distributed normally for the quadratic model with the 23rd data point removed, which is great. This is the first model that does actually conform to that assumption, so suggesting that probably this model is the best one that represents the data. And then I just wanted to show a side-by-side comparison of the 4 models that I tested for their adjusted R squared and whether or not they conform to the Shapiro-Wilk p-value for the normal distribution of errors. So again, the only model that conformed to the normal distribution of errors was the one highlighted in blue at the bottom, it was the quadratic model with the 23rd data point removed. But this model also has the highest adjusted R squared. So going forward, this is the model that I would pick for actual analysis. And then I also used ANOVA, analysis of variance, on the linear and quadratic models, both with the 23rd data point, but to validate that the quadratic model does actually have a relevant quadratic term. So the low p-value, the probability of an f statistic greater than f, the 0.001273, that low p-value is telling us that we should reject the null, the extra parameter is not significant, which is a rather convoluted way of saying that the beta 2 parameter is significant and we do actually need to include it. So in conclusion, the linear model was not the best. The quadratic model is better, as shown in the line above. However, the original research paper from the Hungarian chemist just blindly chose the linear model with all data points in, so that model did not conform to the necessary assumptions, and it wasn't the best fit by adjusted R squared. So I would recommend going with the quadratic model, but in answer to the original research question, if there is a correlation between cystine content and the age of wool, yes, undoubtedly, whether you model it linearly or quadratically, there is a relation. And then in suggestions for future work, 23 data points isn't very many data points, but of course it's probably difficult to get samples of antique carpets. And then also I would check the other three chemical compounds, the cysteic acid, methionine, and tyrosine, to see if there is a better linear fit or just a better adjusted R squared to help determine the age of the carpet. So thank you for your time and attention, and that's it.